Okay, section 8.3. Today we're going to be looking at trigonometric integrals. So everything that we do is going to have trig functions in it, which I know are y'all's favorite. And we're going to want to remember our derivatives and our antiderivatives for those. And also quite a few of the identities that we have seen are going to be utilized in this section. In particular, the Pythagorean identities. We're going to use and lean into those pretty heavily. And a couple others that we're going to encounter that you don't use on a regular basis, but they're going to be helpful for what we're doing. Okay? So to start with, we're going to take a look at what happens when we have sines and cosines. I told you there's going to be a lot of writing, right? I'm delivering on that promise right now. And you've got another sheet that looks just like this later on. All right, so this is what happens when we have powers of sines and cosines. And this is a guideline thing. So like you're going to go down the list, and if one doesn't apply, you move past it on a problem, and you look at number 2. And if 2 doesn't apply, you move past it, and you go on to number 3. Okay? So it isn't like a list of steps, but it's a list of different options of things to try. So the first one says, what happens if the power of sine is odd? Well, if the power of sine is odd, we save one sign, and we turn all the rest of the signs into cosines. And if the power of sine is not odd, we go to step number 2. Not step, guideline number 2. Number 2 talks about what happens if the power on cosine is odd. Well, if the power on cosine is odd, we save one cosine and turn everything else into sines. And both of these, when it talks about changing things into sines or cosines, just a second. Is it going to work? No, it's not. Where it talks about converting the others into cosines and converting the others into sines. What it's talking about is using the Pythagorean identity that we remember, which is the sine squared of theta plus the cosine squared of theta is equal to 1. That's how we're going to change them in steps 1 and 2. So that happens both here on guidelines 1 and 2 and here. Then step 3 says, okay, what happens if I don't have odd powers then? What am I going to do next? Well, these are called power reducing formulas, and they're on your sheet. At least I believe that they are. Well, a version of them is. So the actual one that I've written on here, as it's stated, is not. They're like the half angle identities. So these are called power reducing formulas. It's all right. This is where they need to be anyway for the time being. So they're talking about what happens when we have even powers of sine or even powers of cosine. And we have the ability to rewrite them without powers of sines and cosines. So we can change sine squared into 1 minus cosine of 2x, all right? So it's double the angle divided by 2. And very similarly for cosine squared, it looks almost the same except it's got a plus on the top instead of a minus. Okay, so these allow us to move from something that's squared into something that's not squared. And these are trig identities that, depending on when and how you took trig, you would have encountered in a trig course. Okay? They're called power reducing. And then after you do that, you will convert to an odd power of cosines and apply number 2. Because now you'll have only cosines that are involved. Potentially some powers of cosines still, but they'll be odd. So that's all well and good, except that I bet that you couldn't take that and just do it, because that's a lot, right? It's a lot of instructions on what we're supposed to be able to do. So we're going to take a look at how we actually do that. And I have either 2 or 3 examples for each one of these different direction sets that we have. So here's our first one. Okay, so we go down our list of guidelines, but here's our original problem. It says that we have the integral of sine cubed 2 theta square root cosine 2 theta d theta. Okay, so going down our list, we start at the beginning. It talks about the power of sine being odd. And we have that on this problem, right? So this is an example that's going to use guideline number 1. I've got a power of sine that's odd. Everybody good so far? So we're going to use this power of sine that's odd, and we're going to save one of them. What does that mean? Well, what it actually means is that I'm going to break this sine cubed apart into sine and the other 2 of them, so sine and sine squared. That's what it means to save a sign. It means I want to keep one of them, and I want to have whatever else remains be the rest of it. Right? So if this said sine to the 5th, I would have a sine, and I'd have a sine to the 4th. If this said sine to the 11th, I'd have a sine, and I'd have a sine to the 10th. Everybody with me on that? But the reality is I really want this sine of theta, and you'll see why in a little bit, to sort of be grouped at the end with my d theta. So the part at the beginning, I needed to make one adjustment. I'll fix it in just a second. The part at the beginning will have the squared sign. Okay. The adjustment that I need to make is that there's also a double angle involved in this. This doesn't just say sine squared of theta, it says sine squared of 2 theta, right? Okay, so I actually want all of these to say sine squared of 2 theta. The 2 is not a big problem. It's going to affect it slightly, and we'll see how. But this is what we have so far. And then the piece in the middle, that's still the cosine of 2 theta, doesn't change the moment. We'll figure out how to deal with that in a second. So this is the saving the sign part. But that's not all that guideline 1 said I'm supposed to do. I'm supposed to save a sign and what? Convert the other piece to cosine. So I want to use the Pythagorean identity to change sine squared into something that involves cosine instead. What would it be? What is that? Close. 1 minus cosine. Yes. So we're going to change this now into 1 minus cosine squared, and the angle will stay the same, 2 theta. And then I have the square root of the cosine of 2 theta, and I have my sine of 2 theta d theta. Okay, is everybody good so far? All right. So why in the world did I want to save a sine theta? The reason I want to save a sine theta is because there's going to be a u substitution. And the u substitution is going to have u be equal to the cosine of whatever angle that I'm working with. So check it out. If I let u be the cosine of, and it is 2 theta because that's the cosine angle that I have, right? It's 2 theta. What is the derivative of cosine of 2 theta?
Is it squared cosine?
Nope, we're just going to use cosine 2 theta, no squareds. We'll get the squared still in there, but when we do the u substitution, we'll still have a piece that's squared. What's the derivative of cosine of 2 theta?
1/2 sine 2 theta.
Okay, so let's start with the cosine. What does the cosine's derivative become?
Negative sine.
Negative sine. Okay, so there will be a negative and a sine of 2 theta. Like, that's part of it. And there will be a d theta. And so then I heard 2 different things happening in terms of my 2 theta. What's the derivative of 2 theta? 2. So I'll have a 2 here, because the derivative of the 2 theta, it's a chain rule, right, is a 2. But if we take a look at this piece at the end, it doesn't quite match my d theta, right? It's this part of the d theta, this part of the d theta, but I don't have the negative and I don't have the 2. So I'm going to divide those to the other side, so I'm going to get the 1/2 that you were thinking about as well. So this will have a 1/2, it'll be a negative, there's d theta, or du, and it's going to be the sine of 2 theta d theta. So as I'm making my substitution, this yellow part will become du with a negative 1/2 in front. So that's my derivative portion from my u substitution. The other piece is, because Adrian's right, we have a squared in the cosine, we're going to have a squared on u. So I have 1 minus the cosine of 2 theta is being squared, which means now the u, which is what I've called it, is going to be squared. And I have a square root here as well, and the u underneath my radical. Okay? So what's the benefit? Well, I've turned it into something that has no trig in it, didn't I? Braden's like, yeah, absolutely. And there's no trig in that one. Okay, we do need to simplify some algebra over here, though. We don't have a trig thing to simplify now, some algebra to simplify. But it's not too bad. In fact, instead of writing u square root, you might choose to write that as u to the 1/2. We've done that many times. So I'm going to rewrite it that way, or at least think about it that way. I have my negative 1/2 at the beginning. We would distribute our u to the 1/2 through our parentheses. So we're going to have u to the 1/2 at the beginning. And then what will my power on u be on the u squared now? 5/2, yeah. So I have 2 and I have a 1/2, that's 2.5, right? If you just think about adding like mixed numbers, 2.5. 2.5 as a improper fraction is 5/2. So this is u to the 5/2, and then I have my du. Now, it may not be your most favorite thing to take an antiderivative of, but it's probably not your least favorite either, right? We can work with this. This is a power rule, and we're going to take our antiderivative. My negative 1/2 at the beginning will just come along for the ride. What's the antiderivative of u to the 1/2? Somebody's saying it. 2/3. What's next?
U to the 3.
U to the 3/2. Abstraction sign. What about my u to the 5/2? 2/7. U to the 7/2. And plus c, right? Don't forget the plus c. Adrian can talk to you about it later. Okay. This negative 1/2 is going to get distributed through. So we're going to get negative 1/3 u to the 3/2. I'm going to distribute the 1/2 through, so I have 1/2 times my 2/3, so the 2 is going to cancel. Yes. No, I'm glad you pointed that out. That's what's happening, you bet. The same thing will happen with this 2 in the denominator and the 2/7. So I'll end up with, it'll actually be a positive because I have a negative on the outside and a negative on the inside, 1/7 u to the 7/2 plus my c at the end. Am I done?
Now I got the 100%.
No, it's a u substitution I did. I need to put it back in terms of what u is equal to. And what was u equal to? Cosine 2 theta. So we'll do one quick rewrite step and then we will be done. So this is negative 1/3 cosine of 2 theta to the 3/2. And then plus 1/7 cosine of 2 theta to the 7/2 plus c. Given the magnitude of the things that we're doing, I'm fine if you want to leave it like this. You don't have to put it back in radical form. If you were looking at some other versions of it, or if you're trying to do something inside of WebAssembly and it spits out something, it might turn it into radicals. So you might have some square roots involved and things like that instead of it being written as a power of 1/2, or sorry, 3/2 or 7/2. But I'm going to be good with us stopping here. Sound good to you? Okay, let's try another one. You might notice this one doesn't have thetas, it has alphas. That's sort of irrelevant, but it's fine. We can do that. So this one says I have the cosine to the 4th of 3 alpha d alpha. Okay, so thinking about my guidelines, I do not have a power sign that's odd, so it's not guideline number 1. Number 2, my power of cosine is also not odd, so it's not number 2. And the reason I'm not doing one like number 2 is because it looks just like doing one like number 1. The process feels almost identical. You're just making the substitutions to a cosine value instead of a sine. It's almost an identical process, okay? But this one is like number 3. Number 3 says, what happens if everything's got even powers, right? Now, we don't have a power of 2 on our problem. Ours is a power of 4. So we're going to have to make an adjustment for that, but we are still going to be doing it with the method of number 3 in mind. Everybody good? Okay, so over here, what it says I need to do is I need to think about this cosine to the power of 4 in terms of something that would be squared instead. So in particular, depending on how much you need to see or think about, this is basically saying that I have a cosine squared. Actually, let me write it like this. Cosine of 3 alpha squared, and then it's squared. That's what powers of 4 are, right? You're squaring something twice. Right? My kids are working on, or actually it was a tutoring person I was working with, working on powers of exponents recently. Or that didn't sound right at all. Working with powers or exponents recently and the properties of exponents, right? So a power to a power is multiplication. We've broken this apart. Now, this piece here in the middle, whether it's written like this or with the 2 in between the cosine and the 3 right there, that's what I'm able to do with guideline number 3. I'm able to rewrite it. So let's take a look back over here. It says, if I have cosine squared, I can rewrite this as 1 minus cosine. What happens to the angle? It doubles, right? It doubles. Now, our angle will need to double as well. Adrian's already telling me over here it's a 6, and you're right, it will be. I'm going to double my angle, and then I have division by 2. So this step will take that piece that's in red and rewrite it. It's 1 was minus, wasn't it? Plus, thank you. 1 plus cosine. I double my angle. My angle was 3 alpha, so now my angle will be 6 alpha over 2. And all of that is squared d alpha. Okay, we good? Good so far. I'm not particularly loving the fact that this is a fraction. So if you don't want the 2 down here, you're welcome to pull it out in front, but it's not going to be just a 2 when we pull it out in front. What's it going to pull out as? Nope. Nope. 1/4. Thank you, Pierce. 1/4. The square will apply to it, right? So in some sense, if you want to, I'll write it out this time. So I have 1 plus cosine 6 alpha squared, and it's over 2 squared, or 4. So I'm going to pull it out as a 1/4 in front. And if you don't want to pull it out and you want to leave it there, that's fine as well. I'm also going to write this step down, but just this one time. We're going to encounter this later. I won't write it again. But I don't want you to do what many of you probably tried to do at some point along the way with me in Calc 1 and square each component, right? Yeah. All right, so we're not going to do that. When we have a quantity that's got addition or subtraction in it, oops, that's supposed to say d alpha at the end. When we have a quantity that's squared with addition or subtraction, we have to FOIL, right? There's no distributing a square to each individual piece. Okay, very good. So we have our 1/4. If I do first, outer, inner, last, this is going to give me a 1, because 1 times 1 is 1. On the inner and the outer, they match. And they're going to be cosine of 6 alphas, so I'm going to have 2 of those. So plus 2 cosine of 6 alpha. And then plus the cosine squared of 6 alpha d alpha. Okay, is that okay? All right. We can take an antiderivative of the number 1. We're good with that. We can take the antiderivative of the 2 cosine 6 alpha. It's a simple u substitution. We probably won't even write it. Maybe I'll write it for this first one, but we won't write it typically. But what about the cosine squared of 6 alpha? I'm back down here in 3, aren't I? I've got an even power on cosine. So I'm going to do step 3, or not step 3, but guideline 3 again for that piece. Now, before I do that, let me just rewrite what I have so that we can see it a little bit more clearly. Let me use another screen. I think I have another one, so. Yep. So we can separate these out. In fact, if you want to put the 1/4 back in, you can, but I'll leave mine out in front. So I have a 1/4 of 1 d alpha plus a 2/4, I'll pull the 2 out, 2/4 or 1/2 of the integral of the cosine of 6 alpha, and then plus my 1/4 of my integral of the cosine squared of 6 alpha d alpha, right? That's a property of integration we saw way back in chapter 4 in our book. The first one's manageable, the second one's manageable, the last one needs a u substitution, but a trig substitution involved, okay? So we're going to go ahead and let's just integrate. Let's just go from left to right. We'll integrate what we can, and we'll make the substitution where we can. So this is an in-between kind of step. If you wanted to do all the antiderivatives later in one step, you could do it that way too. But what is the antiderivative of 1? Just x, or in our case, we're using alpha for our variable, so it would be alpha. So this is 1/4 alpha. This is a 1/2 here because I have a 2/4. Let me make mention that this is a very simple u substitution. If I were thinking about this in u substitution and u is 6 alpha, what would du be? 6 d alpha. And I would move my 6 as a 1/6 to the other side, right? So anytime I have an angle measurement that's not just the variable, I end up with a reciprocal of that value multiplied, or I end up dividing by that value. So if you recognize that, you could actually skip doing this because it's that simple of a u substitution. So you have your 1/2, and then you're going to have a 1/6 coming from really like the inverse of the chain rule is what it really is, right? That's what u substitution really is the inverse of the chain rule. If I took the derivative of 6u, it'd be 6, so I do the antiderivative, I get the dividing by 6 part. And then what's the antiderivative of cosine? It's sine. So this is sine of 6 alpha. So that's the piece right there. And then the ending piece needs a substitution. So I'm going to substitute the cosine squared in as 1 plus cosine of what?
12 alpha.
12 alpha, thank you. Right, I double the angle anytime I use that guideline number 3. The angle gets doubled. So my angle was 6 alpha. My angle now will be on this part 12 alpha over another 2 d alpha. Okay, is that all right? Notice I didn't say, do you like it? That's not what I said. Is that all right? Do you understand where we are? Okay, good deal. All right, so I have a 1/4 alpha. I have a 1/12, plus a 1/12 sine of 6 alpha. And then if you wish, you can put that 1/4 that's in front with the 2 that's underneath. That would give you a 1/8. All right, so what's the antiderivative of the 1? I've moved the 2 out from underneath, just the number 1. That's alpha. What's the antiderivative of cosine of 12 alpha? Say it louder, Sophie. Yep, 1/12, and then sine of 12 alpha. I think we got it all written in, right? And plus c. Is that all right?
Yep.
Those pieces?
Yeah, that's all right.
Okay. Then we're going to distribute this through, clean it up a little bit, and we are going to have one piece that's going to be able to combine, not a lot, but one. So I have 1/4 of alpha plus 1/12 sine 6 alpha. I have plus 1/8 alpha, and then what happens when we multiply 8 and 12? 96. That's what I was thinking. 96 sine of 12 alpha plus my c. What can be combined? Yeah, the 1/8 and the 1/4 alphas. So what happens when I add 1/4 and 1/8? You get 3/8. Good. 3/8 of alpha. If you're looking at that and you're like, how'd they do that? Just grab a calculator. It's not a big deal. We're not going to belabor the point right now. So why can I not combine the sine value parts? Like, what is it about that that's causing problems with this one?
Coefficient from the alpha.
It's not, yes, okay, you got to the alpha part. Yes, it's the different coefficients inside of the angle, right? One of them is 6 alpha. It's an angle that's a 6 alpha. The other angle is a 12 alpha. So I can't combine them directly. We will actually see a place later where we can combine something. That's not the point here in this particular problem. We're only going to combine things when it's helpful to keep moving forward and actually do something to do an antiderivative, but at this point we would stop on this particular problem. Okay, so not that I expect you to do this, but if you wanted to make sure you did it right, what could you do?
Take the derivative.
You could take the derivative. And if you took the derivative and you collapsed things down enough with some trig properties and so forth, you'd end up back at cosine to the 4th of 3 alpha, right? Yeah, you would. Crazy. Okay, that's sines and cosines. So why in the world do we group sines and cosines together? Well, the reason we actually do it is, well, there's 2 reasons, I should say. One reason is because we have this beautiful Pythagorean identity that says the sine squared is equal to, sine squared plus cosine squared equals 1. So that's one of the reasons. But the other reason is that they have these very nice relationships where they take derivatives and antiderivatives and just go back and forth, right? Okay, so we have another pair that does that very well as well, and that's tangents and secants. Now, it's not the same relationship, and it's not the same going back and forth, but there's some similarness to them, which means they get grouped together. So if we have tangents, powers of tangents and secants, we have another list of different guidelines that we're going to follow through and see what happens. So the first 2 look much like the first 2 on the other guidelines. They talk about the powers being certain ways on certain features. So if the power on secant is even, we save a secant squared, and then we convert things into tangent. And if the power on tangent is odd, we save a secant tangent, and then we convert the rest into secants. So those two are similar to the one we had before. There is some differences. The reason that there's differences is because, right, the derivative of tangent's not secant, the derivative of secant's not tangent. What is the derivative of secant? Secant x, tangent x. And what's the derivative of tangent? Secant squared. So do you see why we've got a secant squared showing up now? Because it's going to be a derivative of something, right, namely tangent. And why do we have a secant tangent showing up? Because it's the derivative of something, namely secant. So that's why those pieces are showing up. We do have a Pythagorean identity for these as well. I know it's written on your paper, but I'm going to write it in here too. So what is the Pythagorean identity for tangents and secants as they relate to one another? I signed the right way. This will help on these parts where we convert the rest. Do you see it? Tangent squared equals 1 plus secant squared. Okay, so it's not secant plus tangent. It's not secant squared plus tangent squared like it was sine squared plus cosine squared, but they have the components that are squareds in there.
Would it be secant minus 1?
No, it isn't. At least that's not what I have written in on my paper. Oh, I have it written backwards. I put the plus 1 on the opposite side. No wonder. My paper looks like this.
Yeah.
That's where I want it. I just moved too quickly. Thank you. So if I want to solve it for secant squared, it's already solved. If I wanted to solve it for tangent squared, I'd move the 1 to the other side. I would have a minus 1. Thank you. Okay, so that's steps 1 and 2, or guidelines 1 and 2. Guideline 3 says sort of like, well, what happens next if those two things don't apply? Well, what happens if there's no secants, which would mean it's not the secant even part, and the power on tangent is even, right? It's not tangent odd like in guideline 2. So when that happens, we're going to convert a tangent squared into a secant squared, Pythagorean identity. So this conversion stuff is still happening, right? There's a conversion piece in guideline 3. Number 4 is your new favorite tool to use. If you actually have only secants, right? Not only tangents, but only secants, number 4, you're going to end up using integration by parts, but it tells you what dv is. It's integration by parts with dv equal to secant squared, okay? And then when all else fails, this is like back in trig when you're doing identities. If you did that, I hope you did. If you can't figure out what to do, we usually default to trying to turn things into sines and cosines and see if we can find something to do in that realm. Do y'all remember that at all from identities? Okay. I know it would be high school because none of you took trig here, did you? I don't think so. So so turning things into sines and cosines is sort of our last ditch effort because nothing else worked. All right. Okay. You ready to try some? Let me pause for just a second. Sophia's still writing. You good? Okay. Okay, so I'm going to pause and let you look at this one and figure out which of the guidelines we're doing. Which one is it? It's the first one. Not ingenuity. I was not very good at making you work hard when I created my problems. They just go in order today, right? We did 1 and then we did 2, or 1 and 3. And now we're doing 1 again. Okay, so this one says I've got a power of secant that's even. It is guideline number 1. What it says I'm supposed to do is save one of the secant squareds and then convert the other pieces. So saving one of the secant squareds, we did this before, but let me remind you. This means that I break this apart into one of them having secant squared and the other one being everything else, which is secant to the 4th, of whatever angle I'm working with, and this one happens to be 3x. One word of caution, I don't really care about what variables you use, but WebAssign does. So if they give you things with alphas, make sure you're using alphas in your answer. Otherwise, it's just going to bark at you and tell you you're wrong. And you're going to be like, wait a minute, I know I did it right. Just pay attention to the variables they use. If you switch variables for me, I don't care. But This one has x's. We'll use x's. Okay, so we're going to save the secant squared 3x grouped at the end with the dx. So at the end, I'm going to have secant squared 3x dx. That's the saved piece, right? So I'm not going to mess with this at all. And the part at the beginning is going to be, I'll just write it right now as secant to the fourth 3x. It's the part that needs to be manipulated. So this piece I need to manipulate using the tangent squared plus 1 equals secant squared Pythagorean identity that we saw before. So I'm going to replace secant squared with tangent squared plus 1. Notice you can't just decide that you're going to replace secant to the fourth with tangent to the fourth plus 1. Like, that's not a thing, right? You can't just swap out the 2's and the to 4's. Like, that doesn't work. It looks a lot like what we did with our previous problem where we say, okay, this is secant squared squared. So secant squared is tangent squared of my angle, which happens to be 3x plus 1, and then that has to be squared. And then my piece at the end that remained the same is still there. Okay, so inside here, this piece is secant squared, and then it's squared. That's why it's secant to the fourth. Can you see why this actual replacement is equivalent? It's really important. It's okay? If you need to see more steps to see it replaced, show more steps so that you see where it came from, okay? So then, we're going to do like we did on the last problem. We're going to FOIL this, right? We're going to multiply it by itself, but I'm not going to write it out this time. We've done that once. We're going to move forward. So if I do tangent squared times tangent squared, I will get tangent to the fourth of the angle 3x. My inner and my outer terms are these two multiplied and then times 2. Well, I'm multiplying 1 times tangent squared. That's not very exciting. That's tangent squared. And then I have it times 2, so this will be a 2 tangent squared of still the angle is 3x. And then at the end, I have 1 times 1. Okay, so it's like really tempting to say, well, let's just distribute that. Don't do that. The whole purpose in saving this, sorry, not that. Yeah, that was it. This piece at the end is that it does not get distributed. So don't mess with that piece. You're saving it to be used with a u substitution. In particular, at this point, that's going to be the du part, or at least portion of it, okay? So we need to use the other portion in the parentheses to figure out what u would be. So on this one, what would our u be using that first parenthesis piece? Or let me ask it differently. What would I have to be doing in order to get this one to be some version of secant squared? I'd have to do, not tangent squared, just tangent. The derivative of tangent is secant squared. Now, I need my angle to match. So the derivative of tangent is the saved piece that I have at the end. Like, that's why I'm saving it, is so that I have the du there. But the derivative of tangent of 3x is not exactly secant squared 3x. I also need a 3, which will become a 1/3 on the other side. Yeah, so there's a 3 right here. I'll put it in here, and then we'll move it as a 1/3 over to the du side. Okay, everybody good? That u substitution allows me to rewrite my trig integral in maybe a polynomial type of form on this one, actually. The last one wasn't. I had different powers that weren't polynomial-like, but at least something that uses a power rule. So the part at the beginning will have a 1/3. The part at the end in the yellow will actually be my du part, correct? Okay, in between here, I'm supposed to be replacing u for tangent. The first one says tangent to the fourth, so now I will have a u to the fourth. The next one has a 2, and then tangent squared, which will be u squared. And then I have a 1, which is still just 1. And lo and behold, I do have a polynomial. And at the very least, I will typically at this point have something I can do with simple power rules. So we're going to do the antiderivative for a power rule function. What's the antiderivative of u to the fourth?
U to the fifth over 5.
Okay. u to the 5th over 5, or 1/5 u to the 5th. How about 2u squared? 2/3 u cubed. Heard that. And u will be last. Antiderivative of 1 is u. And I need a plus c. Am I done? No, but I'm really close. I mean, I need to distribute the 1/3 through, and I need to replace the u back for tangent, right? So I have my 1/3 times my 1/5. I'll do both of those at the same time. So I have a 1/15. And this is tangent to the 4th of 3x. Plus, now I have a 2/3 times a 1/3. Yes, thank you. Not looking carefully. Tangent to the 5th. All right, I have a 1/3 times a 2/3, which gives me a 2/9. Tangent, we'll get the right power this time, to the 3rd of 3x. Plus, I have my 1/3, and then it's just tangent of 3x. And plus c. Okay, are we good? All right, second example in this set. We have a secant to the 5th of x tangent cubed of x dx. So going back to guidelines, do I have a power of secant that's even? Nope. Do I have a power of tangent that's odd? Did I on that one? I wasn't paying attention really. Yes. Okay, so we're doing step 2, or guideline 2, right? Power of tangent that's odd. And it says if I have a power of tangent that's odd, I need to save a secant and a tangent. So like one of each need to be saved. And then I'll convert the rest of everything else, and they all need to be converted into secants. Okay? Everything will be in secants when we're done, except for the saved secant tangent at the end. So we're going to have a secant tangent at the end of this thing with a dx. So this is the saved piece. I'm going to highlight it to remind ourselves that we're not going to touch it. We'll need it later. What does that leave me with? Well, let's just figure out what it leaves me with first. I had secant to the 5th, so now I will have secant to the 4th, right? I had tangent cubed, so now I will have tangent squared. That's what I'm left with. And then the other part of this guideline says that I need to turn everything into secants, right? Everything into secants. So the first part's good. Secant to the 4th is already in secants. It's the tangent squared part that needs to change. So this piece is going to have to change. And we can use our Pythagorean identities. We just keep going back to the same things over and over again, right? Back to Pythagorean identities. So what is the value of tangent squared of x equal to using the Pythagorean identity? All right, it is secant squared of x minus 1. And I have that secant x tangent x at the end from before. It's still there. Okay. So there is something that's actually nice that I didn't make mention of on this one that's been different than the previous 3. Do you notice my angle's just x this time? I don't have a double or a triple or a 6th angle or whatever like that, so that's going to make this a little bit cleaner. What would I do in the next step, though?
Distribute?
Yeah, we're going to distribute. We need to have some other way of writing this that looks a little nicer. Either you're distributing now or you're u substitutioning and then you're distributing, but somewhere along the way you're going to distribute. This is as good as place as any to distribute. So this would give us secant, we've got to the 6th of x, and then minus secant squared of x. And again, I don't want to do anything with the piece at the end, so I'm going to leave it alone.
Wait, why is negative secant?
Because it should say 4. That's why. Fixed now? This is the zooming in, zooming out thing that I do all the time. I'm sorry. Thank you guys for finding my mistakes. I appreciate it. Okay. But the reason we save the secant x tangent x is because it's going to be at least part of, and in this case the whole thing, of a du. Right? That's why this is here. Hang on. I want more space. So I saved secant x tangent x to be du because whose antiderivative is secant x tangent x? Secant x. And that's the reason why I have turned all of these into secants. That's why. I want them all to be secants so that its derivative, secant x tangent x, is present. So secant x, and in fact, because I don't have any double or triple angles or anything like that, it really is secant x and then secant x tangent x. There's no other pieces that are going on this one at all. So as I rewrite this, what will I replace secant to the power of 6 with? U to the 6th. And how about secant to the power of 4? Minus u to the 4. And then what happens at the end with the secant x tangent x dx? That is my du. And I have another lovely polynomial. Okay, there's only one that we've done that didn't turn into a polynomial. It was the very first one, and it wasn't bad. It was still a power rule one, right? So you should be getting the feeling that these all seem to sort of turn into power rules, and that's pretty consistent. Okay, then, so what's the antiderivative of u to the 6th? U to the 7th over 7, or 1/7 u to the 7th if you prefer. And how about u to the 4th? U to the 5th over 5, or 1/5 u to the 5th, and plus c. And our last step, put it back in, right? Replace the u with what u is equal to. So this will be 1/7 secant to the 7th of x minus 1/5 secant to the 5th of x plus c. Okay, you ready for the most interesting one of the day? Tanner first. Yes.
I guess could you just show the guidelines for a second? I may have mine.
Oh, yeah. No, you're fine. We're going to need them here in a second, too.
So I know why it worked out there at the end, because we had all secants and we just converted them to u's.
Yes.
But why, when we had secant to the 6th minus secant to the 4th, does that not fall under the first guideline?
So we don't need to make any adjustments because we've already made the adjustment. Okay. So we only go back to our guidelines when we're stuck in a position where we can't make any more progress. And in fact, that's a really good question because we're about to see it happen in the next problem.
Okay.
So hold tight to that thought. We will need them sometimes, again, in the middle of a problem to do something with them. But if we don't need them, then we don't go back to changing anything because we've already made our changes. Yeah. Okay, you guys ready for the next one? Most interesting one yet? I mean, kind of. Okay. It's the most different one yet. Okay, taking a look, I've got secant cubed of x dx. Jot that down and then flip back to your guidelines. Which guideline is this going to use?
4.
It is. It's going to use number 4. Which says, what are we going to do? Integration by parts, right? Okay. There's a pattern to the way the book puts these in your book, right? Like, we need integration parts to do this, so it has to come before, right? That kind of stuff. All right, so what it says we're going to do is that we're going to end up needing a dv that's secant squared. Okay, so let's come back over here. We need to let a u and a du and a v and a dv be present. And it's telling us what dv is. It always will be this way. The dv is what? Told us it was secant squared. Okay, that guarantees 2 pieces of information from there. It means, remember, we put things along the diagonal u, v, dv, right? This diagonal right here is the one where we put things that have to equal the original piece. So this determines what the u is. Knowing that dv is secant squared means I actually also know now what u is, but it depends on the problem. So what will the u be in this problem? Just secant. Okay, everybody good with that? Secondly, knowing that my dv is secant squared also tells me what v is, and it's always the same. It doesn't matter what the problem started out as, right? I shouldn't say it quite like that, but it doesn't matter what other pieces are in the problem. If I have secant squared as dv, then I know for sure what the v is. What is my v? It is tangent. Okay, so all those pieces are very quickly determined just by knowing which guideline we're working with. Now, the last piece, the du, may or may not be straightforward. It just depends on the problem, right? It depends on the other pieces that are there, and it will change from problem to problem. But what is the derivative of u? That is, what's the derivative of secant? Secant x tangent x. Okay, everybody good so far? Integration by parts is all about determining which pieces go where. And then once the pieces go there, we're actually able to rewrite our problem by doing u times v. That's the first step. So I'm going to have secant x tangent x and minus, and then I do the integral along the other diagonal that I didn't put things in along, right? This diagonal. So this is the diagonal I'm going with next. So multiplying the v and the du gives me tangent squareds, a secant, and a du. So I don't know what order I would necessarily want to write it in. I'll write it in the order I just said. Tangent squared of x, secant of x, and dx. Now, there's nothing to do in the first part. Did I mess something up?
Should it be dv?
Yes. No. There's a dx missing, though. I don't have space. So we put things in along u dv, and then we multiply along v du. And there's a dx that I had missing. That's the dx that shows up at the end. So I didn't have that off. I left this off, too. Man, I'm just missing my dx's everywhere. Okay. The first part with integration by parts is already done, right? There's no integral to take here. This is just part of the problem that I'm done with, right? I'm finished with that piece. The other piece, though, I may or may not be able to do right away. I may have to go back to guidelines to figure out what I'm supposed to do when I have tangent squared and secant. And that's exactly where I am now. So now, there you go. Tanner, we're back to looking at guidelines. Tangent squared and secant. What do I do next? It's number 3, which we haven't done yet, right? What does number 3 say I'm supposed to do? Turn it into secant squareds. I want to eliminate tangents. Now, that's not going to feel very helpful, but it will be helpful shortly. So just bear with me on why that's going to be helpful.
Why can't we use number 3 since there's a secant x in there, though?
That's what we're using. We're using number 3.
But it says that there is no...
Oh, there's 2 guidelines. There's 2 pieces. It says if this one's happening or this one's happening. So it says if there are no secants so we aren't technically using number 3. We are still going to turn it into secants squareds, though, to eliminate it. So just bear with me. We're not really using guideline 3. I forgot. I'm sorry. It looks a lot like guideline number 3. It's still what we need to do in order to feel out what happens next. It's going to turn into something that you saw. Hopefully you watched the rest of 8.2's video and saw something like this happen. But just patience for a second, and we'll see what happens next. All right, this part at the beginning stays the same. Secant x, tangent x. And I want my tangent squared to become something with secant. So what does it become? Secant squared of x minus 1. And I have my secant of x dx. We're going to distribute this. Okay? I know it sort of feels like we're not making any progress. We will. If I distribute this, I have the integral of secant cubed of x. And then I have minus secant of x dx. And what I'm going to do next is I'm going to separate the 2 pieces that are here and see if you notice something. Still have my secant x, tangent x at the beginning. Now I have an integral of secant cubed of x, and I have plus the integral of secant of x dx. Now I can take the integral of secant of x dx. It's not one of our favorite ones to do, but it's on our list. right? So one of the ones you've been working on your gateway stuff, right? But what about this secant cubed?
Back to the fourth. Back to the. Oh wait.
Back to the beginning.
That's just the original.
That's where we started. So it starts to feel like, did I just circular reason what I just did? Right? So this reminds me, my husband has been preaching a lot out of Galatians, Philippians, Ephesians, Colossians, Philemon, I don't know, Paul's letters, the Pauline epistles, okay? And one of the things he keeps asking the congregation is, why does God love us? And the answer is, because he loves us. That's just it. That's the answer. Why does God love us? Because he loves us. What do we do for secant cubed? Well, we tried to do a bunch of stuff and we ended up getting secant cubed back. So what do? What's that? You move it over. And you saw that happen in the part that I actually posted. I'm going to rewrite the original question I gave you down here. It was the integral of the secant cubed of x dx, right? That's where we started. We don't always think about this as sort of an equation, but it is. This is where we started and this is where we are right now. And Sophia's exactly right. This secant cubed piece needs to be added to the other side, much like in an equation would do in an algebra course, right? If I have an x on the x and I have an x on the left and I have a 3x on the right, I need the x's grouped together. That's what I'm trying to solve for. So we're going to add the secant cubed of x, which is missing its dx. Let's try that. To the other side. And I end up getting 2 times the integral of secant of cubed of x dx. And it equals secant x tangent x. And then now's as good a time as any to actually find what is, well, these pieces add to 0. What is the antiderivative of secant x dx? The natural log of the absolute value. Some of you are getting your absolute values on your gateways too, by the way. Secant of x plus tangent of x. Yeah. And what else do I need? I need plus c. I don't have any space, so I'm going to create some. Plus c's. Okay. I'm not quite done, though. My goal, what I was asked to do at the beginning, was to find out what is the integral of secant cubed, right? Right now, that's not what I have found. I have 2 integral of secant cubed. So what's my last thing I need to do? I need to divide by 2 to get it back to being what I wanted it to say on the left-hand side, which is where I started. So this becomes the integral of secant cubed of x dx, and we will divide by 2 on everything. So I have 1/2 secant x tangent x, and I have plus 1/2, or you can write it as a denominator if you wish, natural log of the absolute value of secant x tangent x. And while it is not wrong to write c over 2, it's also not necessary. C is just an arbitrary constant anyway, so you can leave it saying plus c and it'll be just fine. But if you wanted to write it as c over 2, it wouldn't be wrong.
It's a lot of letters.
It's a lot of letters. It is. Okay, are you ready to look at an easy one, though? Because the next one doesn't have a whole bunch of guidelines. It's actually really easy. All ready? Okay. There's a set of, these are called product to sum or sum to product identities, depending on which direction you go. The ones that are written in here are written in the direction that takes a product of trig functions and turns it into a sum. What do you notice is different about these than anything we've worked with today? There's something uniquely different that says, I have to use this.
There's no powers.
Okay, there's no powers. That's true. There's something else, though, too. Okay, what things are different? Okay, keep working with that. Sophia's noticing that something's different. What's different? The angles. The angles are different. Do you see that? We haven't dealt with that before. We had it at the very end of one of our problems, and I just told you, let's just leave it. It was this one right here where I had, the answer is over here, where I had a 12 alpha, and I had a 6 alpha, and I was like, you can't really combine those very nicely, and we're not going to mess with it right now. We're going to mess with it in this problem, but you're going to like it. Okay? You're going to like it. It's going to be really good stuff. Okay. So when our angles don't match, And we're still multiplying, like that's the other thing too. There's no powers, like Pierce said. There's multiplication, right? I'm multiplying sines and sines. I'm multiplying sines and cosines, or I'm multiplying cosines and cosines. Those are the only options, okay? There's no secants, there's no tangents involved. This is just sines and cosine stuff. But the angles not matching is really sort of like the straw that broke the camel's back of what we need to do with this, okay? So when this happens, we turn our product into a sum or difference. So on the first one, it's 1/2 cosine of, and I subtract the angles, minus cosine of adding the angles. The second one, when it's sine and cosine, I actually subtract the angles, add the angles, but it's with sines. And then when I have 2 cosines, I have subtract the angles, add the angles, and it's with cosines. Okay? So they're all slightly different, but they're all pretty much the same too. Right? The formulas are different, but they operate in much the same way. So they allow us to reconcile different angles. So take a look at the next problem. It's exactly what this looks like, right? I have a sine and a cosine, they're multiplied. There's no powers, and the angles don't match. Now, I recognize that one of the angles is negative, and there's 2 ways that we can deal with that. Right now, we're going to sort of ignore it and do it one way, and then I'm going to show you how you could actually think about it and do it a different way too. Neither one's really easier or harder. It's just a little different. Okay, angles don't match, and it's sines and cosines. So sines and cosines means I'm in the middle, right? This is the piece where I'm at. It says I'm going to have a 1/2. I'm just going to put my 1/2 on the outside of the integral. And then I'm going to have 2 sine values. The first one's subtracting on the angles, and the second one's addition. It doesn't really matter, though, right? I'm going to be adding these together. So if you did the adding of the angles first and the subtracting second, it'd be okay on this one because addition is commutative. The order doesn't make any difference. So if you wanted to do it in the other order, it wouldn't hurt anything. So I'm going to have a 1/2 out here. I'm going to have an integral. And I'm going to have the sine. And I'm going to have the sine of the angles added. So I realize this is maybe belaboring the point a little bit, but I'll write it in for this problem, and then you can feel free to do what you wish in the future. I need to add them for 1. And I need, wait, did I say subtract? I subtract them for 1. We'll do subtraction first. Subtract them for 1. And then I need to add them for 1. Okay. Is that okay? All right, we can add, we can subtract, that's not a problem. So, and maybe you would have jumped to this step immediately, which of course is fine if you did. This is the sine of what? Negative 7x. And then plus the sine of what? Negative x. Okay, is everybody good? All right, take a look real quick, and this is the point where we're going to deal with the negatives in this perspective anyway. If you take a look at your trigonometric identities, right underneath the Pythagorean ones is something called even-odd identities. They tell you what happens when you have a negative angle. So in some of our problems, sine is one of them. I started to say some of our problems. Some of our trig identities, sine is one of them. We have what's called an odd function. And when a function is odd, one of the things you might remember from the algebra course is that it's a rotation of 180 degrees around the origin. That's what it means to be odd visually. It means that your negative angle inside is the same as having a negative on the outside. And that works for sine, it works for tangent, and I think it works for their reciprocals. Yeah, so sine's reciprocal is cosecant, so it would be true for cosecant. Tangent's reciprocal is cotangent, so it would work for cotangent. So those 4 are called odd functions. Negative on the inside just moves to a negative on the outside. The others are actually nicer. Cosine and its reciprocal secant are even functions. So even function, you want to sort of picture in your mind like a parabola, just a normal parabola, like the original parabola centered around the x-axis. It's the mirror image on the left and the right. That's what it means to be even. There's symmetry across the y-axis. When that's the case and there's a negative angle, it's the same as if it were a positive angle, and it sort of just looks like it disappears. So if these had said cosine of negative 7x, I could just write cosine of 7x. And if it said cosine of negative x, I could just write cosine of x. So that one's really friendly as well. This one doesn't say that, but it's odd. And so it's nice enough for us to actually adjust this and to pull this out and to write this as the negative sine of 7x. And then minus the sine of x dx. And if you want, you can pull the negative out in front with your 1/2 as well. That'd be fine. Alrighty then, I'm going to pull my negative 1/2 out in the front with the the negative out in front with the 1/2 at this point. What's the antiderivative of sine of 7x?
Negative cosine.
Okay,
What is it, the 1/7 thing?
yes,
Yeah.
there you go, 1/7, and then it would be negative cosine. I'm going to put the negative at the beginning.
Well, that'll be positive because they have negative sign.
It will, once I distribute my 7th, or my negative 3, you're right. Okay, so I pulled my negative out here. If you had left your negative in here, it'd cancel right here. It's going to cancel somewhere. And I have my cosine then of 7x. What's the antiderivative of sine of x? Which is now a positive because I pulled my negative out. Maybe I shouldn't have pulled them out, but what's the antiderivative of sine x? Yeah, it's actually negative cosine of x. Plus my c. If I distribute my 1/2 through, or maybe you didn't just have it that way as it was, we should have 1/14 cosine of 7x, and then plus 1/2 cosine of x plus c. Okay, so you can deal with the negatives in this way. There's actually maybe a slightly easier way to deal with the negatives if we had done it from the very beginning. So let's check that out real quick. We won't do the whole process, but I just want you to see what it would look like. If we'd seen that negative 7 or negative 4x at the beginning and dealt with it here, that negative could come out here instead. And I could rewrite this as sine 4x cosine 3x dx. And then when I actually add and subtract these angles, they would have already been positive to begin with. So the the sine of 4x, I'd have my negative or my 1/2 out here. And then I'd have the sine of the angles added or subtracted, which would be 4x minus 3x, which would be x. And the angles subtracted, which would be, subtracted was what I did first. Added is what I did second. 7x dx. And you see the same pieces showing up. You'd still end up with the same spot at the end. So somewhere along the way, you have to make concessions for the negative with the even odd identities. Okay. What do you think? It's a lot. This is a big section. There's a lot in it, okay? But lean into those guidelines. Figure out. Don't go out of order either. You got to start at the beginning, and if it doesn't work, go to guideline 2, go to guideline 3 as you're making your way through, okay? Okay, so we only have